We're going to look at an exercise now that's a little bit different than the ones we've seen so far. This is the integral from 0 to 1 of x divided by x squared plus 4x plus 13 dx. At first glance, we notice the denominator does not factor. We cannot use partial fraction decomposition, so we must go a different route. I noticed something a little bit interesting about the terms we see, x squared plus 4x. And if we focus on that, then we might be thinking about, we could turn that into a perfect square trinomial, and we would end up with a denominator of u squared plus a squared. If we had a denominator that looked like that, we might be able to do something a little different. So, considering the denominator, x squared plus 4x plus 13, we know that to complete the square, we could add and subtract 4. I would suggest we have x squared plus 4x plus 13 can actually be expressed as 4 plus 9. In any case, we have x plus 2, the quantity squared, plus 3 squared, if you will. Or 9, doesn't really matter. I'll rewrite the integral from 0 to 1 of x divided by now the quantity of x plus 2 squared plus 9 dx. And now we're going to consider a substitution. We're going to let u equal x plus 2. Then du is equal to dx. Further, if u is equal to x plus 2, then x is equal to u minus 2. We can then rewrite our integral as the integral of u minus 2 divided by u squared plus 9 du. And then we need to convert our limits from x to u. X went from 0 to 1. When x is 0, u is 2. When x is 1, u is 3. And so our limits of integration are from 2 to 3. Now we've kind of made this look a little bit better. We used to have x over x squared plus 4x plus 13. Now we have u minus 2 over u squared plus 9. We made the denominator look a little better, but the numerator look a little bit worse. We are now going to split this up into two separate integrals. From 2 to 3 of u over u squared plus 9 du minus the integral from 2 to 3 of 2 over u squared plus 9 du. For the first integral, if we let u equal, that's not going to work. If we let t equal u squared plus 9, then dt is 2u du. Therefore, since I have a numerator of u and we have a du already, I need to multiply and divide by 2. The first integral will then integrate to 1/2 times the natural log of u squared plus 9. That'll be evaluated from 2 to 3. The second one's going to take a little bit more work, so I'll just rewrite it. Minus the integral from 2 to 3 of 2 over u squared plus 9 du. If this integral had a denominator of u squared plus 1, with say a 2 in the numerator, that would integrate to an inverse tangent function. That would be kind of cool. We could make that happen if 9 were a 1. We are then going to divide by 9 in the numerator and denominator. So let's do this kind of on this side. So as an aside, the integral from 2 to 3 of 2 over u squared plus 9 du, multiplying by 1 over 9 in the numerator and denominator, will become the integral from 2 to 3 of 2/9 divided by u over 3, the quantity squared, plus 1 du. We now consider yet another substitution. I know, it's a lot to keep track of. You can always rewind if you need to. If I let s equal u over 3, then ds is equal to 1/3 du. I'm then going to factor the 2/9 that we have in the numerator into 2/3 times 1/3. The 1/3 I'm going to keep with the du, and that'll become our ds. The 2/3 I'm going to bring out front. So we have 2/3 times the integral of, do I want to do another full substitution? I may as well, I'm already here. ds divided by s squared plus 1. Since s is equal to u over 3, our limits from 2 to 3 will become now from 2/3 to 1. But now we have something that we can integrate straight away. This is going to be 2/3 times the inverse tangent of s from 2/3 to 1. Now all of this that we just did replaces the second term of what we had been working with. So we finally have 1/2 times the natural log of u squared plus 9, that'll be evaluated from 2 to 3, minus 2/3 times the inverse tangent of s, and that'll be evaluated from 2/3 to 1. As we evaluate this, we are going to end up with 1/2 times the natural log of 18 minus 1/2 times the natural log of 13 minus 2/3 times the inverse tangent of 1 plus 2/3 times the inverse tangent of 2/3. The inverse tangent of 1 is, of course, pi over 4. And we can combine the natural logs. My final answer is going to be 1/2 times the natural log of 18 over 13 minus pi over 6 plus 2/3 times the inverse tangent of 2/3.